Right, we're on to the next page of the physics homework booklet for Unit 1 of the BTEC. And there's just one part that I didn't actually get around to doing last time, but then we'll look at the exam style questions. There's just a bit about identifying gases and how they do it. So really we're just saying apply a high voltage to a gas. And then in the lab, you remember, you looked at them when we had the lights off, it makes them glow. So makes them glow. Then you looked at it through the little diffraction grating, which is like an aperture. So look through an aperture, which is a little gap, and the technical name of the piece of equipment you used was a diffraction grating. And then that gives you that nice little spectrum where you can start, experts will start to identify gases, looking at stars and things like that. So this will give you a spectrum. And so now here are some exam style questions that you will have attempted. Which one of the arrows A, B or C shows the wavelength? So we should have this here, so that's going to be B. Incidentally, A would be the amplitude, and C, well, that would be half a wavelength, so it's just going from the bottom to the top, so from the trough to the peak, so it's only half. Question 2. An instrument produces a note of 700 Hertz, and what does that frequency mean? That means 700, and then the Hertz is 700 waves past that point each second. So pass a point each second, so you get 700 waves per second. And then if the sound wave travels at 340 meters per second, calculate the wavelength of the sound. Give your answer to 3 significant figures. Well, we are going to use our standard equation that you should be totally happy with by now. And it says calculate the wavelength. So we want the wavelength on its own, so we're going to rearrange this, divide both sides by f. So v divided by f equals lambda. I'm just going to turn that round because I like it on the left. V divided by f. Lambda we don't know, but that will be in meters. V, velocity, we have 340 meters per second, and frequency, well, it told us 700 into 700 Hertz. So now we just need to 340 divided by 700, put that into our calculator. Here's the trusty calculator. 340 divided by 700 equals 0.48571442. But it does say 3 significant figures. So 485, oh hang on, there's a 7 after it. So we're going to have to round that up. So it equals 0.486, and the units are meters. Question 3. Use the letters to complete the sentences below. Right, and we're sticking the relevant wave in there. So we got the wave with the highest frequency. So that is how many waves we get in a second. So we can see C is more, the wiggles are closer together, so the peaks are closer together, so that's higher frequency. The wave with the smallest amplitude, remember the amplitude is how high the waves are from the equilibrium position. So B and C are quite big, A is the smallest. So those were pretty straightforward. Question 4. Analyse the waves to the right and answer the questions. What characteristics are the same for the two waves? Well, if we look at this, the peaks and troughs, the trough and the peak there are in the same sort of position. So the distance between them along the wave is the same. So we can say there, the same, we can have wavelength and frequency. And what characteristic is different? So we can see one is higher than the other, so that's got to be our amplitude. Question 5. Answer the following question. Use the diagrams. What name is given to a process that happens when light enters the glass block in diagram A? So we've got all sorts of things like reflection, refraction, diffraction, all sorts, critical angle. And the one we're going to choose here for kind of the bending of the light towards the normal is refraction. So I'm going to put that there, refraction. Why doesn't the light change direction when entering the glass block at B? Well, it's travelling in a straight line along the normal, straight at the block. So it's just going to carry on along that normal. So that light ray is already travelling along the normal. So already travelling along the normal. So it can't bend towards the normal because it's already on the normal. Question 6. The image to the right shows a wave spreading out after passing through a gap. What is the name of this process? Well, we've discussed this in an earlier video, and now we've got diffraction. So we're definitely not going to get that confused with refraction. 10 waves pass through the gap every second. The wavelength is 0.02 meters. Calculate the speed. Right, let's use our standard equation again. V equals F lambda. Calculate the speed. Do we need to rearrange this? No. Let's put down what we know on the right. So always a good system of doing it. The speed and the velocity, that's the thing we're finding out, but it's going to be in meters per second. And frequency. 10 waves pass through the gap every second. 10 waves per second. So that's going to be 10, and waves per second is hertz. And lambda. Oh, it just gives us a wavelength, that's handy. 0.02 meters. So we just slip those in. 10 times by 0.02. You do that in your head. So that's 0.2 meters per second. And that's our answer there. Extension question. Ooh. The person standing outside the room can hear the sound coming from the speaker inside the room. The door is open. How? Well, our waves are travelling through the door, the gap, that aperture, and then they diffract and spread out. So just like this diagram here. So the sound waves travel through the open door, which is an aperture. Then they spread out by diffraction. There we are. End of that little quick quiz.